In this video, we'd like to decide whether the vectors u, v, and w lie in a common plane. The idea is to consider the parallelepiped or slanted box determined by the three vectors. So let's just draw sort of a generic picture here. We've got vectors u and v in 3D. And we've got this third vector w that most likely does not lie in the same plane as u, v, and w. So let's say there are three vectors situated in space. Now, these three vectors here determine a box. We can first look at u and v and think about the parallelogram that they determine. So think of that as the base of the box here. And then think of w as describing the third type of side there. And again, we can trace out that parallelogram determined by u and v. So there we go. There's a rough description of our parallelepiped, or slanted box if you prefer. So let's think about the volume of the parallelepiped. If the volume, I'm just going to call it a box, a slanted box for short here. If the volume is equal to 0, then the answer to the question will be yes. Yes, the three vectors lie in a common plane in that situation. If the box has 0 volume, then the box can be contained entirely within a two-dimensional plane. So I'll just draw a representative sketch underneath this here. Let's say here's vector u, here's vector v. Vector w would lie in that same plane. If the volume of the box is not equal to 0, then the answer to the question is no. We could draw the plane defined by the first two vectors, and this time we'll label them u and v. If the volume of the box is not equal to 0, then w must be either extending above or below that plane to create that non-zero volume. All right, so the volume of the parallelepiped, or you could just say volume of the box, is defined as the absolute value of the following determinant. It's the determinant of the matrix which has u, v, and w in its rows. So in this particular case, we've got the absolute value of the determinant of the following matrix. Now, before we jump into this calculation, let's do a little recap of how to calculate the determinant of a 3 by 3 matrix. Let's say we want to calculate the determinant of the following matrix, A, B, C, D, E, F, G, H, I, and we're going to do what's called cofactor expansion along the first row of this matrix. So often I'll just circle that first row here. Now we're going to take the entry in the upper left hand corner, so that would be A, and we're going to multiply A by the 2 by 2 determinant that results when we cross out the row and the column that contains A. So the 2 by 2 determinant that results is the determinant of E, F, H, I. Now we're going to move across that first row, and we're going to build up this sort of sum. And the thing that we have to be careful of as we build up the sum is that the signs alternate as we build up the sum. So instead of writing down b, we're going to write down negative b times a 2 by 2 determinant. This time we're crossing out the row and the column containing b. So we've got the 2 by 2 determinant d, f, g, I. And again, the signs continue to alternate, so now we're back to plus c times the 2 by 2 determinant that results when we cross out the row and column containing c, which is the determinant of d, e, g, h. So I think really the only tricky thing when it comes to cofactor expansion is just remembering this so-called checkerboard pattern for the signs. The entry in the top left gets a plus sign, so we take plus A, and then we go negative B plus C in developing that cofactor expansion. All right, so let's just put a box around that. That was a little recap, and we're going to pick up with our calculation. So going back to the volume of the box, we've got the absolute value of, well, we're going to go 1 times the following determinant. The matrix will consist of negative 5, 4, 3, 1. And remembering that checkerboard pattern as we expand along the top row, we're now going to go minus 3 times the following determinant, 2, 4, negative 1, 1. And now we're back to the third, or now we're using the third entry in the top row. This entry here gets a positive sign, so it's really plus times negative 1. So in other words, its sign is unchanged. It just stays as a negative 1. Times the following 2 by 2 determinant, 2, negative 5, negative 1, 3. So if you look at our coefficients here, the 1 and the negative 1 have been preserved. The 3 gets its sign changed there. All right, now to continue our calculation, we need to figure out these 2 by 2 determinants. So we're going to be careful to recopy our absolute value sign here. And inside the absolute value sign, we've got 1 times, well, this is negative 5 minus 12, so that's negative 17. And then we've got minus 3 times, we've got 2 minus negative 4 gives us 6. And then finally negative 1 times, we've got 6 minus positive 5 gives us 1. So I've just recopied our calculation from the previous screen, and continuing our calculation, we've got the absolute value of negative 17 minus 18 minus 1. In other words, the absolute value of negative 36 gives us positive 36. So the volume of the slanted box determined by U, V, and W is 36. That volume is not 0. So the answer is no. The 3 vectors do not lie in a plane. So let's write down our answer. No. The vectors U, V, and W do not lie in a plane, or you could say they do not lie in a common plane.